the next step that we need to talk about is the Lensmaker equation, because up to this point we've talked about the focus, but we haven't really defined how to find the focus, the focal length of the lens. So here we're using a double convex again as our standard, and notice that the way that the double convex is defined is with the C1, the center of this lens side here, this on the left-hand side, this surface, and C2 refers to the right-hand side. So notice the orientation. These are considered positive, again, positive orientations. And for the analysis of this, it's pretty involved. It's got a lot of trig here. I'm not going to get into a lot of it. I just want you to be able to know the equation and use it. And what you have is, based on this configuration, the reciprocal of the focal length is equal to the refractive index of the lens material minus 1 times the addition of the reciprocals of each of the radius, the sum of the radius. Now, we can simplify this and make it an expression for the focus. We can combine these two radius, reciprocal sums of the radius, and we can get that the focal length is equal to R1 times R2 divided by the quantity n minus 1 times the quantity R1 plus R2. And that will give us the focal length of our lens. Now, with this being positive orientation, if R1 is negative, then that means that our C1 is going to be on the other side. So this would be negative C1. And if C2 is negative, then it's going to be on the right-hand side, so that's negative C2. So that'll make a double concave lens in that case, because our surfaces will look something similar to this. Now, for the meniscus, one will be positive, one will be negative, and it will really depend upon the way the lens is, how the focal length will be calculated. Could be positive, could be negative. It really depends on the size of the radius. And the other point to take into account or to think about is that the focal length is the same no matter how the lens is oriented. So if you were to rotate this lens 180 degrees, I'd still get the same focal length, because this R1, R2 doesn't really change in this formula. Here I've got a multiplication, that's not going to change. Here I have an addition, that's not going to change the order of it. So the focal length is the same no matter which way you twist the lens. So what ends up happening is that you end up getting two focal points. You get a regular focal point and you get a mirrored focal point that's normally represented by F prime. So this focal mirrored point, this focal prime, is going to be useful when we do ray tracing. So let's discuss ray tracing and then we can get into an example.